Presente, profesor Bayón.
Sí, bueno, vayan poniendo presente en el chat. A ver. Entonces, muchachos, esta es una práctica de práctica. Como ustedes saben, es importante que como magíster, para tener el grado de magíster, ustedes tienen que saber inglés, ¿no es cierto? Tienen que aprobar un examen de inglés, ¿es así o no?
Sí.
Bueno,
Yes.
entonces ahora van a practicar con mucha atención. Ustedes van a encontrar un video, voy a poner un video en inglés sobre detectores, o sea que un tema que ya ustedes saben perfectamente, y luego van a redactar lo que entienden, lo que han entendido de ese tema. Así que tienen que hacerlo con cuidado, con mucho cuidado, ¿de acuerdo? Voy a, voy a, les voy a para que escuche la computadora. Vamos a ver, entonces aquí vamos, ya tengo el video, es uno de los más escuchados.
Hi, welcome back to my video once again. So in this video, I want to talk about nuclear detectors. So nuclear detectors are special kinds of instruments.
¿Me escuchan?
Sí,
Hola.
profesor.
Sí.
Escucha.
That can detect nuclear particles like alpha particle, beta particle, gamma radiation, etc., etc., and can also determine their energy, momentum, direction, etc. So out of the many different kinds of nuclear detectors, there is a class of nuclear detectors known as gas-filled nuclear detectors or gas chambers. And in this video, I want to discuss the general principle and working mechanism of these kind of gas-filled nuclear detectors. So by the end of the video, you'll understand not only the general principle with which these detectors work, but you should also be able to distinguish between different kinds of gas-filled nuclear detectors like ionization chambers, proportional counters, Geiger-Müller counters, and so on and so forth. So let's begin. So here we have a general construction of those kind of nuclear detectors. So here you basically have a metallic cylinder which is hollow from the inside and it is filled with some kind of a gaseous medium like hydrogen, air at 1 atmospheric pressure. And along the center of the cylinder you have a metallic electrode which is passing through it. Now this cylindrical surface is connected to some negative terminal of a voltage supply, and the metallic electrode passing through the center is connected to a load resistance which is again connected to the positive terminal of the same power supply. Now to prevent this positive metallic electrode from touching the negative metallic surface, there is some kind of an insulating material. Now across the load resistor you have some sort of electronics which is connected to it, like some kind of an amplifier or a pulse counter that can basically detect the potential drop that is happening across RL and measure the amount of current which is passing through RL. So what is the principle on which this kind of a nuclear detector is based upon? It is based upon the principle of ionization. So when a high energetic nuclear particle passes through some kind of a material medium, it basically ionizes the material medium. Now what is ionization? It is quite simple. So let's take the example of, let's suppose, an alpha particle which is passing through some kind of a material medium. All right, now alpha particle is quite energetic and it collides with the molecules and the atoms of that material medium, and with every single collision it basically transfers some of its energy to the molecules of the material medium, and this energy is basically absorbed by the electrons in the outermost shells of these atoms and molecules, and if the energy is sufficient enough, the electrons will absorb that energy and become free from the atoms and molecules, thus creating a positive ion and a free electron. Now this kind of collision happens many number of times. So along the trajectory of an alpha particle or other high energetic beta particle or gamma radiation, due to many number of collisions, large number of pairs of positive ions and free electrons are created. So when a nuclear particle enters a material medium, it basically leads to the creation of pairs of ions and free electrons. The greater the energy of the nuclear particle, the larger is going to be the ionization and larger is going to be the number of positive ions and free electrons which are created. Now what happens when these positive ions and free electrons are created in the first place? They are subjected to an external electric field. So as you can see here, the metallic surface is connected to the negative terminal of the battery, while the metallic electrode passing through the center is connected to the positive terminal. So basically you will end up getting an electric field along this particular direction. So you will get an electric field which is directed from the metallic electrode towards the metallic surface. So every time some kind of an external nuclear radiation enters this material medium and leads to the creation of positive ions and free electrons, then these charged particles are now subjected to this electric field. So what happens is that this electron will now experience an electric field towards the metallic electrode, and it will experience a force where the force is basically given by the electric charge multiplied by the electric field, and then it will accelerate towards the electrode while the positive charge will be accelerated towards the metallic surface. So all the ions and free electrons which are created during the primary ionization process when an external nuclear radiation interacts with the material medium, so these primary ions will be attracted towards opposite polarities of the metallic electrode and the metallic surface. So after some time, all of these free ions which were created will get accumulated along the metallic electrode as well as the metallic surface, and all these electrons which get
¿Me escuchan? ¿Hola?
Sí, profesor.
Sí, profesor.
Ya, pero esta solamente es la cámara proporcional. Ustedes han tomado notas de las diapositivas anteriores, ¿no?
Sí.
Tienen una idea de todos los detectores un poquito. ¿Pueden hacer un resumen de 15 minutos? ¿En 15 minutos?
Creo que sí.
¿O desearían que lo pasemos de nuevo al anterior?
Sería mejor el video anterior que lo pase nuevo.
Ya,
Sí, profesor, este último video muy rápido habla.
pues,
El anterior está más entendible.
a ver. ¿Qué pasó? No hay sonido.
No, el principio del video,
Hello,
profesor, es así,
viewers.
ahí recién empieza.
Welcome to EPG Pathshala of Biophysics. My name is Dr. Manoj Semwal. I am a medical physicist at Army Hospital Research and Referral, Delhi, Kent. A medical physicist is a physicist who applies the ideas and concepts of physics in medicine. And today, in this module, I am going to talk about radiation detectors. As the term indicates, detectors in various forms and in various spheres of radiation applications are required not only to measure the amount of radiation, but also at times to alert us about the presence of radiation, because whether we like it or not, radiation is ever present, whether it's natural background radiation or because of human-induced activities. So we need to be aware of radiation, because radiation not only has advantages, but it has proven to have negative effects. For example, radiation can cause cancer. In one of the modules, I have discussed about radiation carcinogenesis. Then radiation can cause severe injuries like burn, almost looking like burn injuries. You may be familiar about a lot of radiation accidents. And what radiation are we talking about? We are here not talking about radiation like light, which we all are familiar, because this also is radiation. Here we will be talking about radiation which can cause ionization, because it is the ionization capability of radiation which causes harm. Similarly, it is the ionization capability of radiation which is useful in detecting the radiation, because generally we don't see radiation. So we use its indirect effects, for example ionization, and from the amount of ionization we can detect the radiation or even quantify the amount of radiation. Similarly, radiation can cause several chemical effects. So those chemical changes one can measure, and then that chemical system becomes our radiation detector. Similarly, there are many other mechanisms. For example, radiation can cause polymerization. So if we can measure that amount of polymerization, that again will become a dosimeter, radiation detector or dosimeter. So we require radiation dosimeters wherever we use radiation. Let's have this clear. And based on that only, we will be able to not only detect, we will be quantifying it, and since we know that radiation is harmful, we will be able to protect ourselves. Also, radiation is extensively used in medicine. Most of you are familiar, where you have seen X-rays, chest X-rays commonly done. It involves radiation. Similarly, you might have heard about computerized tomography. That also involves radiation. Then you might have heard about radiotherapy, where radiation is used to treat cancer. In all these processes, we need to quantify the amount of radiation that is given to a patient for treatment or for diagnosis. How do we do that? To quantify that, we need to first detect it and measure the radiation, right? So measurement either can be done by, as I told you, by its ionization capability or its chemical changes that radiation produces. So in this module, I'll be talking to you about various mechanisms of radiation detection and what are the various type of radiation detectors employed. The objectives of this module on radiation detection are to familiarize the viewers with various radiation detection mechanisms, detectors and dosimeter based on these mechanisms, advantages and disadvantages of detector systems. At the end of the talk, the audience will have ideas about the radiation detectors and their applications in a given situation. Now viewers, let's first get it sorted out. What are the types of radiation we are talking about, whose detection we would be talking about? Radiation, ionizing radiation can be broadly classified into two forms. One is charged particulate radiation. For example, electrons, beta rays, or heavy charged particles like protons, alpha rays, other energetic ions, cosmic rays. And then another category could be uncharged radiation. For example, electromagnetic radiation like X-rays, gamma rays, or neutrons. Now, where do you encounter ionizing radiation? In addition to the natural background radiation, which include cosmic rays, radon in the dwellings, or, for example, monazite sands in the Kerala coast, we encounter ionizing radiation in almost all aspects of human activities, such as medical application, industrial application, and research. Now, what type of detectors are available with us? Depending upon the effect of the radiation being observed, the detectors can be categorized as ionization-based detectors. And the most popular among them are ion chambers, Geiger-Müller counters, and semiconductor diodes. Then detectors based on the excitation caused by radiation. And the detectors based on these excitations are thermoluminescent detectors, commonly known as TLDs, optically stimulated detectors or OSLDs, and scintillator detectors. So this is the category which falls in based on the mechanism of excitation. Then the third category of detector could be depending on the chemical changes that radiation produces. And we all are familiar with films, how radiation can cause darkening, for example, on the photographic film. Similarly, radiation can cause, even ionizing radiation can cause darkening of films. So films can be used to detect radiation. Similarly, there are certain gels which can also be used because radiation can set in the process of polymerization or certain other changes, and then those gels can also be used as radiation detector or dosimeters. Then the biological effect of radiation we have discussed in another module. For example, in the module on radiation carcinogenesis, radiation can cause biological damages or biological changes. Detectors based on biological changes, for example, chromosome aberrations. Radiation can cause chromosome aberrations. So if we can measure those chromosome aberrations, we would be able to detect the radiation and the dose absorbed by that particular radiation. There is one more way of categorizing the radiation detectors. For example, we can say gas-filled detectors, for example, ion chambers and GM counters, solid-state detectors, for example, diodes, scintillators, TLDs and films, and liquid detectors in aqueous form, for example, aqueous chemical detectors and liquid scintillators, etc. Now, what should be an ideal radiation detector? So everybody would like to have a detector which can be used in any situation, any condition. So that detector should have the properties, for example, it should be compact and rugged, its response should be stable with time, and even changing environmental conditions, for example, high humidity, high temperature, etc., should not change its response to radiation. Then it should be energy. Whatever radiation we are using, the dose it should show should be independent of the energy of the radiation. Similarly, at what rate the radiation is falling on it, its integral response should be independent of the dose rate. Similarly, this ideal radiation detector should have high efficiency. It should have fast response time. It should not happen that it is irradiated now and that it takes a lot of time to see the radiation response. It should not itself suffer radiation damages. Otherwise, over a period of time, the response of the detector will change. Important another factor, it should be low cost and it should be convenient to use. But the bottom line is there is no ideal universal radiation detector. Gas-filled detector, how do you design it? If you fill the gas in a container, the radiation passing through the gas can ionize the gas molecules. Increasing the amount of radiation will proportionally increase the ionization because this is an ionizing radiation. The charge thus produced due to ionization can be collected using an external electric field. For example, if you have a cylindrical container, you give a positive and negative charge to its outer wall and put on central electrode and apply a voltage between them. So whatever is the charge, depending on its polarity, it will accordingly go to different electrodes. So thus you can collect the charge. The result is, and when you collect that charge, the result would be what? An electric pulse that can be measured by an associated measuring device. So with proper calibration, the value of charge collected on current gives information about the radiation exposure or its strength or intensity. The choice of gas, which gas to fill in a detector, what should be the geometry of the detector, whether it should be a pancake type, it should be cylindrical or spherical, and what should be the applied potential between the electrodes within this detector container gives us controlling power over the properties of the detection system. Now, suppose you have a gas-filled detectors of a certain size and you apply a certain voltage between its collecting electrode. Initially, when you have a low voltage, most of the ion produced by radiation may not get collected. Some of them will recombine if the voltage is not sufficient. As a result, if you keep increasing the voltage between the electrodes, the current or charge collected would increase and ultimately reach a plateau region where the total charge produced by the ionization event has been collected. Okay, so when all the charge collected by the radiation event has been collected, the amount of charge collected would have some relation with the energy deposited by the radiation or the amount of the radiation that fell on the detector. Now again, let's experiment. We keep increasing the voltage between the electrodes. As we keep further increasing the voltage, the ionization produced within the detector would start causing further ionization, because the ions will gain sufficient energy to produce further ionization. As a result, the pulse height, now the amount of charge produced will keep increasing with the amount of voltage you have applied, and this region is then called as a proportional region. It depends not only on the amount of energy spent by the incident radiation, but also the voltage applied. Beyond a certain point, this increase in the pulses would not happen, because sufficient ionization has been produced by the incident radiation, by the ionization produced within the detector. Again, you will encounter a plateau region where with increasing voltage, the pulse height or the amount of charge collected would not increase. And that region is again good for radiation detection. That region is called as a Geiger region. So we have two regions where there is a plateau, where the pulse height does not increase with applied voltage to some extent. Initial region was called as ion chamber region, and then the third region was called, after proportional region, was called as the Geiger-Müller region or the Geiger region. So these two regions are very frequently used for radiation detectors. So let's come to the ion chambers. That means the initial plateau region. What are the advantages? Because as I told you, the voltage applied in this region does not change the pulse height. That means the detector is insensitive to applied voltage. This translates into less expensive power supply. So small voltage fluctuation would not change the pulse size. Similarly, the current saturation voltage or saturation charge collected total, or the current produced by the ionization, is directly proportional to the energy deposited by the incident, because all the ions produced by radiation have been collected. So more the number of ions, more will be the current. Similarly, this detector is less vulnerable to gas deterioration. This we would see later in the Geiger region, where because of the multiplication of ions within the gas deterioration takes place. Hence, change in concentration of electronegative contaminants does not seriously impact the response of a detector based on ion chamber principle. But what are the disadvantages? Low current. That means there is no amplification of current happening here. Whatever is the charge produced by the ions is being collected. So there is no amplification. As a result, the current is low if the amount of radiation falling on it is low. And inherently, ion chambers are low sensitivity detectors. So they are unsuitable for low radiation environments. Another disadvantage, you need to use low noise electronics to obtain good signal to noise ratio, because signal produces low in current value. Similarly, vulnerability to atmospheric condition. For example, if the temperature and pressure within the detector changes, the density of air within it will change. As a result, amounts of ion produced will change, needing different calibration. Preferably used, what is the other disadvantage? Preferably used in current charge modes and not in pulse mode, due to external amplification circuit and its response time issues. Where are ion chambers used? They are, you would see them being used at survey meter around a radiation installation. So ion chambers are used to survey a radiation installation. If there is a radiation generating equipment around it, what is the amount of radiation for protection purposes? Then ion chambers are extensively used as dosimeters for radiation output measurements of equipment used in radiation therapy or radiology, for example, X-ray machine, radiotherapy machines. Similarly, ion chambers are also used as isotope calibrator. What is isotope calibrator? Different radioisotopes will emit different types of radiation, and what is the amount of radioactivity on a isotope that is being used in nuclear medicine or radiotherapy, this isotope calibrator can figure out. Then comes, as I told you, after the ion chamber region, there is a proportional region where the pulse height or the charge collector is proportional to the initial radiation produced. This is achieved by increasing the voltage applied across the gas detector. Why do we do that? To achieve better, as I told you, to improve the signal to noise ratio as you increase the signal height. The process leads eventually to As you keep increasing the voltage, what happens is the primary ions produced by the ionizing radiation starts producing secondary ionization. And as a result, eventually it leads to cascade or avalanche multiplication and consequently a large pulse at the output. Large pulse of what? Current pulse or charge pulse. Okay. Typically, a cylindrical proportional counter is similar to they would look like similar to a cylindrical ion chamber, though with mechanics that can withstand higher electrical potential. How much is the signal amplified in a proportional counter with respect to a normal ion chamber? 10 raised to power 3 to 10 raised to power 4. Output here in terms of charge or current is still proportional to the initial charge produced. Like ion chambers, virtually any gas can be used. However, since the threshold of gas multiplication in noble gases is much lower than in polyatomic gases, the standard practice is to use a noble gas as the main component of the filling gas mixture. Argon, being cheaper, is the most common gas used in proportional counters. Where are they used? Proportional counters? They are mainly used for neutron detections. Boron filled proportional counters are used for this purpose. Why? Because, for example, slow neutrons react with boron to produce alpha particle through N alpha reaction. Now, N alpha particles are charged particles and they are intensely ionizing. So now neutrons are being detected indirectly because they are neutral particles. So with boron they react, a nuclear reaction produces alpha particles. Those alpha particles produce further ionization in the BF3 filled proportional counters, and that current that is being produced is measured. Using a large chamber, for example, a huge spherical chamber filled with BF3, all the electrons generated by alpha particles through unalpha reaction of the neutron can be stopped within the chamber, and we can know energy of the neutron source, because all of the emitted radiation which has produced ionization has been stopped within the detector. So this is because N alpha reaction happens with slow neutrons. What about detecting fast neutrons? For fast neutron detection, you slow them down by using paraffin moderated around this slow neutron detector. Thermal neutron, for thermal neutron you don't fill BF3, boron trifluoride gas, but you fill helium gas. And with helium, thermal neutron react by an NP reaction. That means the neutrons will produce protons, protons being charged particle will produce further ionization. These proportional counters are used for alpha and beta spectroscopy. Advantage of proportional counter over the next ion chamber gas field detector that we are going to discuss, that is Geiger counter, is its short resolving time. That means the time, if two radiation events happen between less than 10 microsecond, then proportional counter would not be able to register them as two events. We will see later the Geiger-Müller counter has this resolving time much larger than proportional counter. So this is because it has a low resolving time. Now coming to Geiger-Müller counter. When the applied electric potential, remember what I told you initially, in a gas-filled radiation detector, if you continue to increase the potential between the cathode collecting electrodes, localized avalanches in the proportional counter spread through the chamber. In the proportional region, the avalanches were localized along the electrodes. But now, with further increase in the voltage, they happen throughout the chamber volume and a breakdown situation reached. Even a single ionization event can cause this breakdown. So even a small amount of radiation incident on a radiation detector being used in the Geiger-Müller region will cause this breakdown within the detector, resulting in extremely high currents. What is the amount of amplification here? 10 raised to power 10. With ion chambers, there was no amplification. With proportional counter, it was 10 raised to power 3 to 10 raised to power 4. And with Geiger-Müller counter or GM counter, it is 10 raised to power 10. So in this case, no need of further amplification. It is useless for spectroscopic purposes because it will not be able to differentiate between two different energies. Both of them are causing breakdown in the entire within the detector, and same amount of pulse pulse height is being achieved for any kind of radiation. Used for particle counting only for counting purposes, As I told you, resolving time or dead time here is very high, between 200 to 400 microsecond. During this period at GMC, GM counter does not record any ionization event, but it is easiest among all three to build. High sensitivity, this can be used. Where can GM counter be used then? As I told you, this is highly sensitive. Even a small amount of radiation can be detected here because the amplification is very high. So high sensitivity, so they are used in high sensitivity radiation survey meter. That means where low level of radiation are expected, you will use a GM counter based radiation survey meter. It can be used for contamination monitors and zone monitors. They come in different forms. For example, cylindrical shape, pancake shaped, N window shape, etc. depending on the application. Now, from the gas field detector, let's come to scintillation detection. What is scintillation? If passage of radiation through certain materials results in emission of radiation in the visible of UV region, that is called a scintillation. Now, this emitted light caused by radiation can be converted into an electrical signal with the help of photodetectors. If you have a photodetector, you may be aware of many photodetectors, you know about photoelectric effect. So, light photon falls on a certain material and the material emits electron. So, you can produce an electrical signal. So, light emitted by ionizing radiation is incident upon a photodetector, and that is measured and in terms correlated with the amount of radiation. And what is used for this purpose is photomultiplier tube. A photomultiplier tube achieves multiplication of 10 raised to power 5 to 10 raised to power 6. Mind you, remember, Geiger-Müller had 10 raised to power 10 amplification. PMT generally has 10 raised to power 5 to 10 raised to power 6. Nowadays, photodiodes are replacing photomultiplier tubes. Generally, high efficiency scintillators emit in the UV range and hence are mixed with another class of scintillators to shift the wavelength to visible range, because visible light detection is easier than UV light detection or cheaper. Decay time ranges from few nanoseconds to milliseconds. That means these scintillators, if the radiation falls at a certain point of time, the light production should happen within few nanoseconds up to few milliseconds. If the scintillation is delayed, which is called afterglow, then that kind of a scintillator will be unacceptable as a detector. Similarly, now we can divide these scintillators into two categories, inorganic and organic, or solid or liquid. Organic scintillators are generally less efficient than inorganic scintillators, but they are not hygroscopic. That means they don't absorb moisture and result in less backscatter, as they are made of low atomic number material like hydrogen. Good for low energy, less penetrating radiation. For example, anthracene, stilbene are organic crystalline scintillators. Among the most popular inorganic scintillators are sodium iodide activated by thallium, cesium iodide activated by thallium, bismuth germanate. They are most popular inorganic scintillators. They are high atomic number, high density. As a result, they are high efficiency radiation detectors. In some other module, you will be knowing how high Z material, high atomic number material, high density material are also high efficiency radiation detectors. In this module, we'll restrict ourselves only to the detection part and not discuss the physics of how radiation interacts with matter. So these scintillator detectors are good for gamma ray detection and spectroscopy. Then there are liquid scintillators. For example, if there is a very low energy radiation such as a beta radiation and you need to detect it from a certain source, you bring a radiation detector close to it. Maybe the beta radiation will not be able to penetrate into the detector to its sensitive volume. So what happens is liquid scintillation come handy there. You mix the radiation emitting source with the liquid scintillator, and after that the scintillator is going to emit light. That light will come out of the container, which is a transparent container, light transparent container, and this light will then fall on either photomultiplier tube or photodiodes and will be detected. So these liquid scintillators are particularly advantageous for low energy radiation such as beta particles emitted by tritium and carbon-14. Then comes another category of detectors called semiconductor detectors. They work on the principle of electron hole creation by radiation, require only about 3 electron volt to create ionization. Please recall or remember that it requires about 13 electron volt to produce ionization in water, whereas for semiconductors it's only 3 electron volt. That means more number of ion pairs will be produced in a semiconductor as compared to a liquid detector. But the problem with semiconductor detector is that they need cooling and very high purity material to reduce thermal noise. What are the materials, semiconductor materials used? Silicon, germanium, gallium arsenide. Silicon is the most common material for detector as it's cheap, but gallium arsenide is used extensively as it has higher photon absorption efficiency as compared to silicon, which has allowed the development of extremely thin, at about 100 to 200 micrometer thin X-ray detectors. So very compact detectors have been developed based on gallium arsenide semiconductors. Another advantage of gallium arsenide is that it can be operated at room temperature, which simplifies the detector design considerably and also cuts down the cost of development and operation. Generally used in diode form as detectors, the depletion layer in the PN junction diode serves as a sensitive volume for detection. What are the advantages of diodes, semiconductor diodes or dosimeter? They are instantaneous readouts, they're compact in size, they're rugged, and they have high resolution for spectroscopy because it requires only 3 eV to produce one ion pair. But what are the limitations? They are energy dependent response, they directional dependence, that means from which direction radiation is falling on the detector. Response might vary depending on the direction. Then temperature also changes their response, that's called thermal effect. And diodes are also known to change their response with time because of radiation damage caused to them over a prolonged period of time. So after talking about gas-based detectors, scintillation detectors, and semiconductor detectors, let's come to another class of detectors called thermoluminescent detectors. Term thermoluminescence stands for thermally stimulated luminescence, which is in simple word means emission of light by thermal stimulation. The usefulness of thermoluminescent material as radiation detector was realized way back in 1950s. Since that time, such detectors are extensively used in dosimetry. It is a class of inorganic materials, insulators and semiconductors. TL dosimetry is used in many scientific and applied fields such as radiation protection, radiotherapy, clinic, industry, and space research using many different materials. There are many different TL materials. Thermoluminescence is based on the band theory of solids. That means there is a conduction band, there is a valence band. Radiation, because of radiation, electrons are emitted from the valence band to the conduction band, and since there is imperfection in the crystal structure, from the conduction band they get trapped in the forbidden band where there are traps available because of the imperfection of the crystal, and they remain trapped there till, because due to heating, or that's what we call as thermal stimulation, these electrons get out of these traps and combine with the holes which are close to the valence band, and during that process emit light. So that is why this is called thermal luminescence. There are many TL materials available. TLD100, commercial name is TLD100, which is a popular TLD material based on lithium fluoride, has a concentration of about 400 ppm, parts per million, of magnesium added to serve as the primary trapping center. What is the sensitivity of this TLD100? About 100 micrograde, which is quite low. So among the disadvantages of TLDs are that it has no instantaneous readout like you have in the semiconductor detectors. Then there is a problem of fading, and hence needs calibration for this also needs for absolute dose measurements, calibration for absolute dose measurement. Then there are handling issues. Scratching on the surface of the TLD may lead to reduction in its mass, or its response may become contaminated by grease or adhesive that can change its response. So these are some of the disadvantages of TLDs. A new category of detectors which has become popular nowadays is optically stimulated luminescence detectors, or OSLDs. What is OS? What is optically stimulated luminescence? It is the luminescence emitted from an irradiated insulator or semiconductor during exposure of light. So unlike TLD where you needed heat to produce light from the trapped energy of the radiation, the material, here you used one wavelength of light to excite the material to emit another wavelength of light. An excitation source here is a laser source which illuminates the sample, and the total light yield is measured with a photomultiplier tube. OSL techniques have advantages over conventional TLD techniques for a number of reasons. The most obvious advantage lies in the fact that the readout method is all optical, requiring no heating of the samples. One of the commonest OSL materials is aluminum oxide doped with carbon. Interestingly, this material started as a TLD material known as TLD 500, but its fading attracted attention towards its OSL property. Now detection sensitivity here can be down to a few microgray, which was about 100 microgray with TLDs, well below with the TL material. So what happens in an OSL material is you have a dosimeter. So after irradiation with ionizing radiation, this is brought to a OSL reader. In the OSL reader, a certain wavelength of light in the form of laser illuminates this sample. As a result, this sample emits light in another wavelength on another wavelength, and that is detected by a PM detector. So in place of a heating, you have a light source which is being used as a stimulant. So OSL nowadays, because there is no heating required, are becoming very popular dosimeters, and they have a potential to become online also, using optical fibers to send light for excitation as well as to collect the emitted light. Another form of dosimeter or detector is film dosimetry. It is attractive due to its high spatial resolution and wide accessibilities, because films are available everywhere. It has short measuring time and being intrinsically two-dimensional and integrating. Film dosimetry is widely used in radiotherapy to obtain the relative dose distribution of electron and photon beams in water, in plastics, and in inhomogeneous medium. In fact, before the use of TLDs became very routine for personal dosimeters in protection, films were used as film. They used to be called as film batches for dosimetry purposes, or radiation protection, personal radiation protection dosimetry. So in the films, amount of radiation fallen on the film results in blackening, and that amounts can be related to the amount of blackening on the film produced, which is called as optical density. And then that film is processed, and one measures the optical density, calibrates that film system, and it can be used as a radiation detector and dosimeter. But the problem with such kind of film was that processing conditions also could change the response of the dosimeter or detector, or temperature of the processing, the concentration of the chemical used in processing, all could be variables in knowing the response of the films. Now a new category of film has come which has obviated the need of processing. They are called radiochromic film. These films use cyanide dye films has resolved some of the problems experienced with conventional dosimeters. The film consists of thin, radiosensitive, colorless leuco-dye bonded on a 100 millimeter thick, micron thick mylar base. They are colorless before irradiation and turn a deep blue color upon irradiation without physical, chemical, or thermal processing. The radiochromic films most commonly used in medical applications are GAF-chromic films like model MD55, EBT2, EBT3. One more class of dosimeters or detectors is aqueous chemical dosimeters, and in that Frique, ferrous sulfate, benzoic acid, xanolol orange, they are some of the dosimeters. What happens here is the chemical change due to radiation is ferrous ions are converted into ferric, and the ferric ion concentration is proportional to radiation dose. These ferric ion concentration can be measured by UV spectrophotometry in Frique and visible spectrophotometry in the FBX case. The measuring range of Frique is 40 to 400 gray, whereas that of FBX is 0.1 centigrade to 3000 centigrade. And mind you that the FBX dosimeter has been developed in India as a modification on Frique dosimeter. It has found many applications in medicine and industry. Then till now we were discussing about point dosimeter or 2D dosimeter. The new class of dosimeters about which a lot of research is going on are gel dosimeters that can be used for mapping three-dimensional doses, because in the gel is trapped the information which is in three-dimensional, and if you can read this information, even ferrous getting converted into ferric, if it is happening in a gel matrix, and later on you can use certain imaging methodology, maybe MRI or maybe CT, to find out this ferric concentration, we will be able to map the dose in 3 dimensions. To summarize, radiation detection and measurement is a sine qua non for safe and efficient application of ionizing radiation in various aspects of human activity. There is no one radiation detector that is useful for all types of applications. Depending upon their properties, several types of radiation detectors or dosimeters have been developed suiting different requirements. Ionization-based gaseous detectors, semiconductors, scintillators-based solid-state detectors, thermal, optical luminescence-based detectors, chemical detectors and dosimeters, and gel-based three-dimensional dosimeters are some of the types of radiation detectors that have found application in diverse fields such as medicine, nuclear power, and research. Thank you.
Muy bien, interesante, ¿no? Ok. Bueno, entonces como ustedes han escuchado, amigos, alumnos, no hay pues una técnica que se aplique a cualquier campo, dependiendo de la actividad, del problema que tienen ustedes al frente, escogerán el más adecuado detector en física médica o en cualquier otra actividad de aplicación de la radiación. Entonces, la primera pregunta que se me ocurre es, si han prestado atención a esta charla, ¿qué detector, qué sistema de detección de dosis o de radiación, sobre todo de dosis, han escuchado en este vídeo que no hemos tratado en clase?
Los de gel, los detectores de gel.
Los de gel, sí. ¿Y qué otro?
Había otro de óxido de fierro. Había
También,
uno de... Ajá.
muy bien. ¿Otro más?
Los OCLs.
No, eso sí lo hemos tratado.
Bueno, no pasó usted un video, pero no lo hemos expuesto. Creo que a eso se refiere mi
Ah,
compañero.
que no lo han expuesto ustedes ya. ¿Otro más? Bueno, uno que no se ha tratado y que en este vídeo se ha tratado muy rápidamente es el daño cromosómico. ¿Alguien tiene una idea de lo que trata este?
¿Hay dosímetros por daño cromosómico?
No, bueno, no exactamente, pero cuando hay, por ejemplo, un accidente, alguien se ha irradiado en una manera elevada, más de la cuenta, y eventualmente hay consecuencias de ello, se hace un análisis cromosómico. Es decir, se toma parte del tejido irradiado, alguna muestra, puede ser de sangre, y se analiza bajo el microscopio. Es un análisis citogenético, es decir, se toman los núcleos de las células, se Es como cuando uno analiza el ADN, ¿no?
Profesor, ¿será un estimado basado en el daño generado en las células?
Claro, lo que pasa es que
Tejido.
con
En el
microscopio,
video decía aberraciones cromosómicas, que es lo que miraban en ese tipo de dosímetros biológicos.
exactamente.
Son cambios biológicos, decía, ¿no?
¿Qué entienden ustedes por aberración cromosómica?
Daño directamente
Cambios, mutaciones,
una
eh,
mutación
una variación en el orden, ¿no? de las proteínas.
Del código genético.
genético, claro.
No, eso ya es demasiado. No, lo que pasa es que ustedes saben, los cromosomas tienen una forma, ¿no? La mayoría es más o menos como una X, ¿no? ¿Se acuerdan?
Sí.
Eh, bueno, estos cromosomas que tienen una forma, de repente ustedes cuentan en el microscopio que de 100 cromosomas, 10 le falta un pedazo. O sea que no estamos acá hablando acá de código, sino de una ruptura de un cromosoma.
A veces cortes en los alelos, esos como bracitos que tienen.
Exactamente, o sea, hay una aberración evidente al microscopio. Entonces, lo que se hace es se cuenta el porcentaje de cromosomas que están dañados, aberración se llama eso, y en base a eso, pues se deduce la dosis que ha recibido el tejido. El porcentaje es demasiado, bueno, hay mucho menos que eso, ¿no? Pero se deduce una dosis. Bueno, eso es a lo que se refiere por aberraciones cromosómicas. En el Instituto Peruano de Energía Nuclear hay un laboratorio que se dedica a estudiar esas aberraciones cromosómicas. Eh, hay un biólogo ahí que se llama Marco Espinosa, que hace ese tipo, está en la sección de protección radiológica, ¿no? Bueno, ese es muy importante porque se nota claramente que ha habido daño elevado. Pero como digo, eso es un análisis que se hace en casos especiales. No sé, no sé, no sé, voy a ver si por acá hay alguna muestra. Bueno, hay una serie de figuras que ustedes lo pueden estudiar tranquilamente, ¿no? Pero era lo que quería señalar, lo que no se ha visto. Bueno, entonces, ustedes tienen una tarea ahora. En el tiempo que falta, van a hacer un resumen rápido de todos los detectores que han ustedes escuchado. Entiendo que a medida que iban escuchando, también iban tomando nota, de modo que esto no va a ser complicado, ¿no? ¿Está bien? Pueden hacer también ¿cómo se llama? Un resumen de lo que han hecho, ya han tomado nota, y ya pues, vamos.
Profesor, ¿el resumen lo subimos al Classroom o cómo?
¿Cómo?
El resumen que vamos a hacer, ¿lo subimos al Classroom?
Claro, pues claro, pero de eso se trata, ¿no? De eso se trata. Claro, vamos a poner aquí la tarea. Esto les va a servir para la práctica, ojos. Así que tómenlo en serio. Tómenlo en serio. Uni. Método. La física médica. Trabajo de clase. Crear. Esta es una práctica. No es calificada, sino dirigida. Pero eso significa que me va a servir para que ustedes muestren que han puesto interés. La nota de las prácticas calificadas a veces son moduladas por el interés que el estudiante pone en el asunto. ¿Mm? Entonces, ¿cuál es la tarea? La tarea es hacer una lista de dosímetros y sus aplicaciones específicas y sus correspondientes aplicaciones específicas, ¿no? Por ejemplo, si ustedes dicen un Geiger, ¿para qué sirve eso? Para dosimetría, ¿para qué? ¿Ah? Hace una lista específicas de acuerdo a sus características. Esa es. Entonces, fecha de entrega. Fecha de entrega es hoy día. Hora de entrega. Como hemos tenido un retraso, va a ser entonces 21:40. Vamos a poner 21:59. ¿Ok? No se olviden que esto le va a servir para mañana, así que estudien. ¿Ah? ¿Alguna pregunta, entre tanto? ¿Les ha servido esta clase hemos hecho de detectores? ¿Les ha quedado claro el panorama de la técnica? Acuérdense, una cosa muy importante que hemos dicho varias veces y que también en el vídeo se ha escuchado y se observa, es que la detección se basa en propiedades propiedades físicas o en procesos físicos, químicos o biológicos, y que la radiación puede ser cósmica, puede ser algo que venga de alimentos, de máquinas, de rayos X, de reactores nucleares, de fuentes radioactivas, de modo que es muy amplio. Y los detectores tienen pues sus características que permiten trabajar con estas aplicaciones con el menor riesgo posible. Esa es la idea. Y ustedes tienen que tener claro en los procesos físicos, químicos o biológicos que están involucrados en el sistema de detección. Notan ustedes que a medida que avanza el tiempo, las técnicas, los detectores son más complejos, pero que tienden a ser más sensibles, de una respuesta rápida, mejor lectura, automatizado en algunas veces, y eso va en beneficio de los usuarios, tanto los trabajadores como los pacientes en la física médica. Y por supuesto también queda el mensaje de que ustedes como físicos médicos y físicos, trabajando con estos aparatos, pueden también captar ideas e inventar algunos nuevos detectores. Es muy importante conocer esto, ¿no? Y por supuesto, en la física médica que ustedes van a ver, van a usar muchos detectores, por ejemplo, para ver la calidad del haz, para irradiar maniquíes antes de irradiar a los pacientes. Y allí pues van a tener que escoger no solamente los detectores, sino también van a tener que hacer simulaciones de procesos de irradiación para calcular la dosis y comprobar esa simulación con detectores, porque los planificadores son, digamos, plataformas, si podemos decir, que simulan, que simulan y con los que se escoge un procedimiento de irradiación. Pero eso tiene que estar validado con una comprobación experimental. De modo que la vida de ustedes va a ser eso, va a ser la comprensión de los procesos, la medición de dosis, la comprobación que están bien con los cálculos, con las simulaciones, para que el paciente reciba la dosis óptima. De eso se trata el curso. En los cursos que vienen luego van a ser mucho más aplicados, más, digamos, más técnicos, porque van a tener que ver con máquinas, con aparatos, con protocolos de irradiación, en el tratamiento del cáncer, en la medicina nuclear, en el radiodiagnóstico. Cada uno tiene sus propias características. Van a encontrarse con la maravilla de la física, porque todo está allí basado en la física. Las fuentes de irradiación, la producción de rayos X, ¿no? Es muy importante, porque a veces cuando los científicos están haciendo sus trabajos posteriores, se dan cuenta de algunos detalles que no son tan simples. Por ejemplo, esta semana que estábamos trabajando una simulación, nos encontramos con el problema de que los rayos X que salen de estos aparatos no tienen una distribución isotrópica, o sea, tienen una distribución angular muy especial, y esta distribución angular hace un poquito más difícil la simulación de la irradiación de un paciente. Pero todo eso requiere pues conocer la física para arreglar esos problemas. Ok, bueno, entonces, ¿alguna pregunta? ¿Todo bien?
Sí, profesor.
Dime.
No, todo bien, profesor.
Ok, entonces los dejo trabajar y a las 9:45 cierro la... Ah, y no se olviden de poner su asistencia. Ponga su asistencia. Entre todos ustedes, ¿hay alguno que tiene, diríamos, dificultades con las notas? ¿Quién tiene problemas con notas? Todos están bien, un poquito tienen esa oportunidad pues para la práctica y el examen final. ¿Mm? Los dejo trabajar entonces. Ah, me olvidé decirle que de las 4 prácticas hay una que se va a eliminar, por si acaso. Ok, entonces nos vemos pues. Si no hay
La,
preguntas.
la más baja, la más baja, profesor.
Claro, pues si tú quieres, te pides que te elimine la alta también, no hay problema.
Ah, profe, no, está bien.
Gracias, profe. Sí,
Pensé que
gracias.
hablaba de un específico. Hasta luego.
Hasta luego, hasta luego.